See. Okay, welcome everyone. If there is anyone in the audience. Discord. Okay. Just a couple things before I begin for today. I added this. Oh, it's on the other side. This link to Ko-fi. I'm not sure how to pronounce it. Um, so that's just a link to support the stream if you want to donate anything. If you want me to go over like a specific problem, and I'm ignoring you or something, or it's a little off topic or something, that might be a way to get it into the stream. Um, Yeah, and then one other thing was Wednesdays. I sort of added like a exercises day, so I'm not really gonna lecture at all. It'll just be kind of a chance for you guys to give me questions that either are from something we're doing right now, like from the Axler book. We can go over some exercises from there that are they could be as difficult as you want, I guess. Or if you just have a problem, like I think Poisoned Mouse sent in some PDE work, which was in Portuguese. So yeah. Today though, I'm gonna talk about. So this will be called Lesson 14, Bases in Dimension, and we're dealing in finite dimensional vector spaces. The reason he doesn't want to go into like infinite dimensional vector spaces is the way he kind of worded things isn't exactly properly correct. So it's a little bit easier just dealing with finite dimensions. I don't know if I like this marker. Let's go. Oh, I didn't get something to erase the board. All right, hold on one second. There we go. Right. So lesson 14. I'll just write bases and dimension. Of a vector space, right? So what is a basis of a vector space? I would say this is probably the most important notion in linear algebra, at least in the abstract course that you would take. So a basis is really kind of what allows us to say that any vector space has certain fixed coordinates with respect to that basis. So first, let's write down what the definition is. So this is on, again, we're following the Axler book. So this is Sheldon Axler, Linear Algebra Done Right. Page 39. And this is definition 2.26. So it says a basis of V is a list of vectors. Sometimes you'll see a basis for V is a list of vectors. And this list is simultaneously what we talked about last time, linearly independent. So that guarantees that every vector has unique coordinates with respect to this basis. There isn't like two different ways to write a linear combination of the VIs. So if the VIs are the basis, there should only be one way to write every linear combination. So first, for a basis, you need this list to be linearly independent. And two, it needs to span the vector space. meaning that if I take all possible linear combinations of this list, I'll get every vector in the vector space. So it needs to span all of V. Okay. Does anybody have a problem with this definition? So basically, it's kind of like a 2-4 definition. It's a spanning set, so it spans all of V. All the linear combinations give you all of V, but at the same time, it's also linearly independent. And these two things imply a uniqueness property. So the first one says that the linear combinations of any vector in the span of the vectors is unique. And the second one says that there is a coordinate for every possible vector. So if it didn't span all of V, there might be some vector that like doesn't get coordinates in this independent system. Okay, so that's basically the main idea. Basis is both linearly independent and it spans all of V. And if we have these two properties, like I was saying, what you get out of this is you get some sort of uniqueness out of the coordinate vectors. And I'll write down what that means. All right, so we haven't proved anything yet about the size of a basis. I guess theoretically here, it's possible that two different bases have different sizes of the list, right? Like one basis might have 3 elements, and then another basis might have 4 elements. So it's not exactly clear that a linearly independent set that spans all of V is automatically always the same size. It's not completely obvious, but obviously that is what dimension means, so we will be arguing that eventually. Is there any questions? Okay, so just to reiterate what we had linear independence and spanning set. So what does the first one mean? What does the linear independence mean? Just to kind of, oh my god, this marker's not good. Let me get a new marker. Also, that was a brand new marker, so I must be going through these markers very quickly. Which is good. That means we're doing a lot of math. So the fact that it's linearly independent, this means, oh wow, let's see, that's way better. Right, that if some linear combination of the vectors from the list equals the 0 vector, that automatically means that they're all equal to 0. So the coordinates of the 0 vector, the only coordinates of the 0 vector is all zeros. Have you met a basis worse than the market? Wait, is this a joke? What's your third favorite basis? Oh, I read that wrong. Have you met a basis worse than that marker? Those are my 2 questions. I feel like I'm not getting this joke. So linear independence means that, or you could think of it as the coordinate vector of the 0 vector is uniquely all zeros. That's another way of thinking of it. And the second one means, so the spanning set means that every vector has some coordinates. Can be written as some linear combination A1. I'll just write tilde since it's not the same one as this necessarily. All right, so if you combine these two together, since we have both of these simultaneously, the first one says that, actually, let me rewrite this. So I didn't want to say this. I wanted to say what this implies, which is that the coordinates are that's not what I wanted to write. So means that if a vector is in the span of the vectors in the basis, then the coordinates are unique. Okay, so let me just summarize what I was trying to say here. So the first one, the fact that it's linearly independent, that the basis is linearly independent, that means that any vector in the span has unique coordinates. So if I pick, there's only one way to write every vector in the span as a linear combination of the VI's. There's no other AI's that give you this same linear combination. And the spanning set says that every vector has some coordinates. So you can think of it as the first one says that the coordinates are unique, and the second one says that every vector gets coordinates. So every vector gets coordinates, and those coordinates are unique. And that's what the basis gives you. Do markers form the basis for all writing surfaces? Right. Okay. So I think we got this straight. So that's what this basis gives you. It basically gives you all of this to say that it gives you unique coordinates for your vectors. All your vectors have can be written as some unique linear combination of the VI's. Okay, and then I'm going to go a little category theory. It's not really category theory, but you know, I'm going to draw arrows, so it'll be fun. Right, so once you fix a basis, like I was saying, this gives you every vector, you can write it in unique coordinates. So one way you can think of that in terms of like, we haven't talked about what a linear map is yet, but actually, yeah, let's think of this map. Let's not even worry about it being linear or not, but let's just think about this as a function. So there's a function. If we have a vector space V and it's finite dimensional and I fix a basis, what this essentially allows us to do is it allows me to take any coordinates, so n is the size of the basis, the length of the basis, and I can take any vector of coordinates a1, a2, an, and I can send it to the linear combination of the basis vectors of these coordinates. So I can just send it to a1, v1 plus a2, v2 plus an, vn. And since these coordinates represent every vector uniquely, you basically can show that this map is one-to-one and onto. So the coordinates, no two different coordinates get sent to the same vector. That means it's one-to-one. And it's onto because it's a spanning set, because the basis is a spanning set. So that means that every vector is some linear combination. So we get this uniqueness of the coordinates and the fact that every vector has coordinates. That's essentially equivalent to this map being one-to-one and onto. So yeah, this map basically gives you a bijection, and you know, I guess the next chapter we'll go into linear maps. We'll show that this is a special bijection, that it's a bijection that's also a linear map, so it's a linear bijection. It's an isomorphism of vector spaces. And isomorphism, if you guys have taken any sort of abstract algebra, isomorphism essentially means that in terms of algebra, the structures are essentially the same. So as far as linear algebra can see, every vector space is essentially just some list of coordinates in Fn. Hello, new chatter. JCYW. Right, so I know maybe this needs to sink in a little bit, but this is actually saying a lot. It's saying we start with an abstract vector space over F. It's finite dimensional. Once I fix a basis, I essentially get an isomorphism back and forth between the vector space and lists of coordinates. And you can call these like the coordinate vectors of the vector. So you can go back and forth. You can take a vector, you can get its coordinates, or you can take a coordinate vector, and once you fix the basis, or yeah, well, you need a basis to go this way too, but once you pick a coordinate vector, then you can take some linear combination of those coordinates and you get a vector back. Okay, so is anybody at all confused about this? Do I need to go over this anymore? Does anybody have any questions? Hello, N simplex. All right, no questions. Okay. All right, and then I'm going to go to 2.31, which is a statement about the basis. And it just says that every finite dimensional vector space actually has a basis. So it's not clear a priori that, you know, this linearly independent spanning set actually exists for every finite dimensional vector space. In fact, it actually exists for every vector space, but you need like axiom of choice or something to prove that. I don't know the exact technical set theory details, but I think you need like some strong axiom of choice, like axiom of, you know, uncountable choice, etc. Right, and I was talking about Rex a little bit about like for infinite dimensional vector spaces, there's a lot of weird cases, like you can have the real numbers are a vector space over the rational numbers, but there's like no basis that you can write down that's intelligible. It's just like some existence proof, basically. So infinite dimensional cases, a little weird, but this statement is about finite dimensional vector spaces. It just says every finite dimensional vector space, it does have a basis. So that at least is easier to prove. You don't need any sort of axiom of choice or anything. Wow, this marker is way better. I'm loving this marker. Yeah, everybody is hanging out here. Okay, yeah, so this is 2.31, Axler, and it just says basis of a finite dimensional vector space. And the statement's pretty simple, just every finite dimensional vector space has a basis. So did anybody actually read Axler? How does this argument go in terms of in terms of this book? And you don't have to get it like perfect, just kind of summarize it for me if anybody knows. So remember, finite dimensional vector space for Axler is just some vector space where there's a finite list that spans the vector space. It doesn't have to be linearly independent, just there's some finite spanning set. So how would we prove some vector space with a finite spanning set necessarily has a basis? How would we show, what's like some ideas that how we might show that? And I'm not going on until I get some answers. So I'll start out the proof basically. So by assumption it's finite dimensional, so there's a finite spanning set. So what does that mean? I don't know if this is stupid, but I think with Rn it's the n part. What do you mean by that, Mouse? That would be more the dimension, right? Here we want a actual basis of vectors. I mean, for Rn there is a basis of vectors that has length n, but here we don't know we're in Rn. It's just an abstract vector space, right? Oops, maybe I'm in the way. So the statement is that every finite dimensional vector space, which is just a vector space where there exists a finite spanning set, necessarily has a basis. Yeah, this is Axler. Yep. Yeah, this is 2.31 Axler, chapter 2. Well, I mean, yeah, you don't have to know the answer. Let's just throw out some ideas. So we know there exists some finite spanning set. How might I show that there is a basis from that? We don't know that the spanning set is a basis, right? Because we don't know that it's linearly independent. Yeah. So that's what it means that there exists a spanning set. So there are vectors v1 through vn such that the span of the vectors is v. Yeah, that's correct. First time chatter and first time correct. I like that. Yeah, so that's one thing we could say. Yeah, so there does exist a finite spanning set, but we don't know it's necessarily linearly independent. So there exists some list v1 through vn such that the span is v. Okay, but that doesn't make it a basis, right? Necessarily. That's just kind of translating spanning set into, yeah, what the definition of spanning set. So yeah, how do we show this spanning set v1 through vn? Well, we can't necessarily show it's linearly independent because it might not be, right? But there's something maybe we could do to this list to get a basis from it, right? So yeah, I'm gonna kind of start from here. I'm gonna erase everything else. We're gonna finish this, or actually I can just erase the top. Well, if it's so trivial, then prove it for me. Yeah. If it's so obvious, then the proof, should just write itself, right? Exactly. Yeah, so how do we prove that? I mean, that is the statement we're essentially trying to prove, right? We want to show that we can cut down this list somehow, that it still spans V, but, now it's linearly independent, right? So I forget, I'm not sure the number in Axler, but he does, there is a theorem that says if you have a spanning set, there is a way to like delete vectors from it without changing the span such that the list at the end is linearly independent. But I kind of want to go through like what is the argument for why you can do that. So we have our list here. Is V1 linearly independent? Just the set, just V1? If it was linearly independent, there's nothing to show, so we can assume it is dependent. Yeah, that's true. Yeah, so if it's dependent, what does that mean? Yeah, get rid of the dependent ones, but like we kind of need some sort of procedure to go through to make sure that they're dependent, right? So I guess the argument in the book sort of follows like you start with V1, right, just v1. If it's linearly independent, meaning it's not the zero vector, then you keep it. And then you go to v2, and then you look at the list v1, v2. Is that linearly dependent? Well, v1 wasn't dependent, we just said. If it was, we would just delete it. Oh, actually, I'm saying this argument. Maybe let me. I wish I had the Axler book in front of me, but essentially, you just want to go through the v1 list, and you're just gonna say, okay, v1, if it's a dependent list, I'll delete it, and then I get a new list, and then I go, okay, now I look at the next one, and I keep extending the list only if it's still linearly independent when I add the next vector. So like you're basically gonna have two cases here. If v1 is not the zero vector, then you look at v1, v2, and you check, is that linearly independent? If it is the zero vector, then you just delete it, and now you just start at v2, right? And then either v2 is not the zero vector, which means it's linearly independent, in which case you would add v3 to it, and you basically just continue this process. Essentially, you keep adding vectors to the list. If the new vector you added makes the list dependent, then you delete it. And you know the list is always linearly independent because you're only deleting vectors that make it dependent. And you can show that this process doesn't change the spanning set, essentially. So there's I'm not going to go through the whole argument, but that's essentially the gist of it. You write down these increasing lists, and every time you add a vector, if it makes it dependent, you just delete. You basically don't need the vector. It's in the span of the previous ones, so when you add it to the list, you're not really adding anything because you already got all linear combinations, and it already includes, yeah. Yeah, so I'm not claiming that this is like a full proof or anything. This is just kind of like the idea of the proof. So hopefully this gives you enough where you could sit down and write this yourself. Essentially, you're what I think what Mouse said is sort of like on the nose in terms of the idea, which is you're just like deleting the dependent vectors, but you still have to check like what is the process to do that, and you have to check that when you do that, you're not changing the spanning set. So it's really, to fully prove it, you really have to write it out fully like that. Yeah, so maybe I'll just we'll write out like a sketch of the proof. Not like a full proof, but, well, really we could just say, use Axler. Every spanning set can be reduced to a linearly independent set that spans the same set. That's the basis. We're done. But really I wanted to sketch like, what is the sketch of the proof of that statement? So I guess we would just finish the proof here. We would say, I don't have the number here, but there is an Axler statement that says every spanning set can be reduced to a linearly independent set without changing the spanning set. So basically we just say reduce this to linearly independent set, and then we're done. So we're going to use, I forget the number of the theorem, but we're going to cite a theorem here, say, okay, this is a spanning set. We can reduce it to a linearly independent set that spans the same set, which is V. So now we have a linearly independent set that spans the set. And now we just want to sketch, what is this? I'll write a star here. What is the sketch of proof of star? And that's just start with the empty list. And then progressively add vectors to the list. Unless they're dependent, then delete them. If list becomes dependent, then delete. Hopefully you can read that. Sorry, what are these questions? He uses V and W. I'm deeply upset about multivariable calculus. Me too. Yeah, multivariable. No fun. Okay, so the clean proof is V is finite dimensional. There exists a finite spanning set. Reduce that spanning set to a linearly independent set, which has less elements, or less than or equal to the number of elements, and then now you have a linearly independent set that spans the same space, and you're done. How do you prove that you can reduce that? Here's like a sketch of the proof. You're going to start with an empty list, and you're going to start adding vectors from your spanning set to the list. Every time you add a vector, if the list becomes dependent, you delete that vector. So the original list is linearly independent, and I'm only adding vectors if it remains linearly independent. So the list at the end of the day will be linearly independent. And then you have to go through an argument. I didn't write this, but you have to go through an argument about why does this reduced list still span all of V, right? Because we got rid of some vectors, so maybe we span a smaller space, but that's just not true. Okay. So any questions about this? I see they're getting into the multivariable calculus. Yeah, so I'll save the multivariable calculus till last. That's my No, I like multivariable calculus. It's not that bad. But okay, so now unless someone wants me to talk about this more, I'm going to go to 2B, section 2B. Or no, yeah. Exercises from 2B, I mean. Right, so 2B, problem 1, I actually wrote this down in the discussion Discord, so I don't think you were supposed to do this, but because he says at the beginning you're supposed to assume F is always complex or real, but I thought it would be interesting if the field was allowed to be any field. It kind of made the problem a little more interesting. So we want to find all vector spaces that have exactly one basis. And remember that a basis is ordered, right? So I know Rex pointed out that if you have a basis of size 2 or more, then you could always just swap any of the two elements, and then you'll have a new basis, right? So that's sort of hinting at if the dimension is 2 or higher, then it's just impossible, right? If the dimension is 1, then over the real or complex numbers, then it's kind of easy to show what happens, but there's something in the proof. So let's prove it over the real or complex numbers, because that's what Axler, I think, intended the problem to be. And then I'll comment about what part, or I'm going to ask you guys what part of the proof actually depends on it being real or complex. So we already said that every vector space has a basis, right? It might be the empty list, but every finite dimensional space has a basis. And I think we're assuming here the vector space is finite dimensional, or else, we haven't really talked about basis otherwise. So find all finite dimensional vector spaces that have exactly one basis. Let's assume F is the real or complex numbers. Right, we already said there's some basis, so there's some list of vectors. So let's assume that beta, which is V1 through Vn, is a basis for V. And then, so how does this proof go? or basically, what does this force to happen if, so let's assume there's only one basis. Assume V has exactly one basis. Okay. Well, yeah, I guess, well, if V has exactly one basis, then I guess this is the only basis, right? Yeah, so what do we know about n then? I think Rex, you actually basically gave me the argument here. So what do we know about n? We know it has exactly one basis, and this is the basis. I'll let you guys ponder. So here it's actually interesting, the order of a basis actually does matter, which is a little confusing, because you would think you just take any set and you could create a basis, but really you have to tell the ordering of the elements. Yeah, the size, so what, Rex, tell us why does the size have to be less than or equal to 1 here? So why does n have to be less than or equal to 1? All right, so if it was, I'll kind of write it over here just as a note. Yeah, if n was 2 or bigger, we could always write down a second basis, beta, I'll write beta 2. So if n is greater than or equal to 2, then the basis, which is v2, v1, vn, that means that this is actually a different basis, because if these are linearly independent, it means that v1 and v2 are not equal to each other, and therefore I can swap them, and this is actually a different basis. It's sort of the same basis, but the ordering is changed, which is technically a new basis because the list is different. All right, so if n is greater than or equal to 2, that's basically a contradiction, right? So that can't possibly happen, because then we would get a second basis that's not equal to the first basis. That contradicts our assumption. Therefore, there's only one possibility, right? N has to be less than or equal to 1. So we have two cases. What happens if n is equal to 1? Well, then our basis just has one vector, v1, or v, or whatever you want to call it. Or we could call it anything in the world, right? So if n equals 1, then our basis is just equal to v1. And so if the field is the real or the complex numbers, what's a different basis that I can form here if n equals 1? It's kind of like you have to think of like, what is the definition of basis? Yeah, you really just need to think about what is the definition of basis? How can I create a new basis if I know that the list of size 1 that just contains this one vector v1 is a basis for v? How could I create a different one? 0. Yeah, 2 times v1. Yeah, exactly. And in fact, I can multiply by any non-zero number, right? So 2 times v1 is a basis, 1/2 times v1 is a basis, I times v1 is a basis, and you could actually show any constant times v1 is also a basis, as long as the number is not 0, because then you would have the 0 vector. 0 is not linearly independent. Right. So if n equals 1 and f is the real numbers or complex numbers, we actually have infinitely many choices for other bases. In fact, I can multiply by any number from the field that's not 0, which there's uncountably many, and I get a different basis. So that's another contradiction in this case. So now there's only one other case. the only other case is that n is 0. Yeah, so n can't be greater than or equal to 2 because we get a contradiction. We can swap any of the basis vectors. N can't be equal to 1 because then we get uncountably many different bases. And then, so n has to be equal to 0. And if n equals 0, then we get no contradiction, because if n is 0, then there's no vectors in the basis. And that just means that there's no other elements besides 0. So every element can be written uniquely with no vectors. That means it's just the only thing in there is the 0 vector. So V is the 0 vector. All right, so that basically shows that if your vector space only has one basis and the field is real or complex numbers, then this is the only option, that the length of the basis is size 0, because if it has at least one element in it, then there's more than one basis. And the vector space that's just the 0 vector, it only has one basis. It's the empty list, and there's no other basis because the empty list is unique. There's no way to reorder anything because there's nothing in it, etc. So what part of this argument fails if the field is not real or complex? That's the question. And Rex, you're not allowed to answer. So it's basically like a 3-part proof, right? We did a what is it called? A I don't know. What does it mean to break it into 3 parts? Trisection? So we broke it into 3 parts. If the length of we know that a basis exists. Now it's just a matter, is the basis greater than or equal to 2 in size? Is it greater than, or is it equal to 1, I mean? Or does the length have 0? It's okay, puzzle, Andy. No guesses. So which one of these 3 doesn't work, basically, is the question. And if you notice, when I said n equals 1, I said we could multiply by any non-zero number and we would get a new basis, right? So the only possible way that there's still only one basis when n equals 1 is if the number of invertible elements in the field is exactly 1, meaning that there's nothing else I can multiply this vector by other than 1. And that's only the case if your field is Z mod 2 and your vector space is Z mod 2, which is like the one case, the one possible case in all the possible fields and all the vector spaces that only has one basis, even though it's a non-trivial vector space. So I thought that was interesting. Figure I'll write it down anyways. And even other fields that are extensions of Z2, they also have other bases because I can pick other non-zero elements. So it's literally just Z2. So I thought that was pretty funny. Yeah, this is undergrad linear algebra, but honestly, like, I mean, I'm not going too complicated in the theory. So even saying it's undergrad, I mean, you could probably listen to me on like your first year taking it, and we're eventually going to get into the standard calculations of solve this linear equation. But I think Axler, when he writes linear algebra done right for this book, like, I think he's correct. Yeah, linear algebra done right, like, this is actually, it's going over the theory more. It's less calculation. You're just saying these are vectors in some abstract space. What is a basis? Dimension is the size of the basis. So we'll get into calculations in a bit, but yeah, I just wanted to write, so only example for n equals 1 is when your field of scalars is Z mod 2Z or F2, which is just 0 and 1, and your vector space is also F2. So every field is a vector space over itself, and in this case F2 only has one basis over F2, and that's the basis, which is just one element, which is 1. And there's no other invertible element I can multiply because F2 only has 2 elements, and I'm not allowed to multiply by 0, so I can only multiply by 1. Right, so basically everything here works for R and C, except if n is equal to 1 and your field is F2, then the argument doesn't work anymore, because you only have one other element to multiply with, and that means there's only one other basis. All right, and then I just kind of quickly wanted to go through dimension, but we've kind of already gone over everything that you need to know to define dimension. Dimension now is just, well, actually no, we haven't. So first we need to prove that every basis actually has the same number of elements, and then we can define dimension should just be the size of any basis, because they all have the same size. Okay, so that's statement 2.34. So now I'm going into 2C on dimension. Uh, 2.34. So it says basis length does not depend on choice of basis. Not. Yeah. Right. So Axler likes to break these proofs into simpler proofs. So here, how he's proving this is really depending on another theorem. So he has another theorem, I'll write it over here, or maybe I'll call it a lemma for our purposes. Even if he doesn't call it a lemma, but so previously he proved that any spanning set or any spanning list is larger than a linearly independent list. So, and this is sort of a, it's another tough proof like the one I was going through with the deleting the dependence. Like, it's not hard to conceptualize, but to write it down formally, it's a little bit annoying. This is another one of those proofs where he's starting with the spanning set, and he takes the linearly independent vectors and he starts adding them to the beginning of the list, and he starts deleting vectors from the end. And he goes through this whole argument to prove that if you have a spanning set and you have a linearly independent list, then the linearly independent list always has less vectors than the spanning list. So I wouldn't say it's like a trivial argument, but you can look it up in Axler. He does go through the proof. I'm not gonna have time to do it here. Like I'm not gonna have time to do it justice here. But you can take my word for it. The main statement we're using here is that a spanning list is larger than a linearly independent list. And so that's essentially going to give us the proof automatically, because we have two lists that are both linearly independent and they're spanning lists. So one list has to be less than or equal to the size of the other list for one reason, and then the other list has to be less than or equal to the size of the first list for basically the same reason. So we have beta 1 and beta 2 are bases. Then the size of B1 or beta 1 is smaller than or equal to the size of beta 2, because beta 1 is linearly independent and beta 2 is a spanning list. So size of B1 is less than or equal to the size of B2 or beta 2. But the argument is symmetric, right? Because B2 is also linearly independent and B1 is a spanning set, so then beta 2 is less than or equal to beta 1 in size. So you get inequality both ways. So I'm kind of running out of room, but same exact argument, just reversed. So the bases have the same properties. They're both linearly independent and they're both spanning sets. So you use this lemma in one direction, you get inequality one way. You use the inequality the other way, you get the inequality the other way. Oh, thank you. Yeah, it's a experiment, you know. A couple of videos a little too dark. You figure out where to put the lights, and yeah, it gets better. Hopefully, I'll get a bigger board eventually. I know my board isn't like super large, so that's one issue I'm gonna work on. Bigger board, better lighting, better camera. That's the goal. Any questions? Yeah, the pen looks really good though. The marker here is very black. Not sure if that's what you're pointing out. Right, so if there's no questions about this, so beta 1 is smaller than beta 2 in size, but beta 2 is also smaller than beta 1 for the same reason. Therefore, they have the same size. Yeah, that's a good question, right? I said I wanted to just stick to finite dimensional, but somebody's asking, is that also true for vector spaces which don't have a finite dimension, like a set of, like an uncountable basis or some countable basis? Yeah, so in that case, I believe the proper statement is that every basis would have the same cardinality. So, you know, in set theory, you have the first infinite cardinal is, you know, the same, it's, you know, I don't know what the proper word is. I want to say isomorphic, but I know that's not correct. But, you know, it's 1-to-1 to the integers, right? Then you have the next infinite cardinal if you assume, what is it, the continuum hypothesis or whatever. There's no cardinality between the integers and then the real numbers, and then you have like the power set of the real numbers and then power set of that and power set of that. So you can go up forever. But I do believe that there is a statement about the uniqueness of the cardinality of the basis. So if you take axiom of choice and all this stuff, then every vector space has a basis, and then I think you can actually show that the basis has every basis has the same cardinality. So you can't have one basis that's countably infinite and then one basis that has the cardinality of the real numbers or something. That's just impossible. Not sure what part of that depends on axiom of choice or doesn't depend on it, but I know if you do take the axiom of choice and all that stuff, then there's no issue. Okay, and then so here, I didn't really write it here, but really our final conclusion is that the size of beta 1 is equal to the size of beta 2. So every basis necessarily has the same size of the list, because remember a basis is a list of vectors. And since the basis has this unique integer size, then we define that to be the dimension. And that's sort of, in some way, it's the unique quality of a vector space that's finite dimensional. It really tells you everything about the vector space. There's nothing else you really need to know. Once you know the dimension is n, then you know that the vector space is isomorphic to f to the n, and you don't need to know anything else. We know how to study f to the n. We know linear transformations between f to the n's are given by matrices. So the fact that this dimension is unique is like actually very important. It sort of it highly restricts what types of abstract vector spaces are even possible up to isomorphism, right? They have to be isomorphic to f to the n because the basis is unique, and you can always define this bijection back and forth between v and f to the n. Okay, so let me just write that final part. I think that's basically it. But does anybody have any questions? So every basis has the same size, and then we call this the size, the length of that list, the dimension of the vector space. Okay, so this is just statement 2.35, which just defines dimension. Or sometimes they write dim v, like that. So the dimension of a finite dimensional vector space is the integer, or the, yeah, I'll just say integer length of any basis. And we just showed that doesn't matter which basis I pick, this number is unique. Right, and then I guess quick example here at the end would be, we kind of already went over this linearly independent set, so Fn is actually is a direct sum of the standard basis vectors. So there's Fe1, direct sum, Fe2, direct sum Fen. And E1 through En are linearly independent. It's easy to show that. They form a spanning set because every vector in Fn is some linear combination of the standard basis vectors. And there's n vectors in this list. So huge surprise here, guys. The dimension of Fn is n. I know it's going to be mind-blowing. Right? Because Fn, we have a spanning set, E1 through En, which has length n, and it's easy to show it's linearly independent. Therefore, it's a spanning set that's finite, so it's finite dimensional, and it's linearly independent, therefore it's a basis. There's n elements, so there's dimension n. And once we know that the dimension of a vector space is n, we know that up to isomorphism it just looks like this vector space. So this is essentially every possible vector space you could have that's finite dimensional is just some list of scalars. That's it. Is that operator standard for direct sum, or is it overloaded? Yeah, this is standard for direct sum. Yeah, or in LaTeX it'll be like \O plus. So it's like a little circle with a plus in it. There's also a circle with a times. That's a tensor product though. That's a different one. All right, so that's it for today. Oh wow, I went like a full hour. All right, so yeah, that's it for today. We'll do a little bit more with dimension. I'll do some exercises tomorrow. I was telling people at the beginning here that I'm going to start on Wednesdays doing just exercises from the Discord. Hopefully they're related to the topic that we're talking about, but I might occasionally take questions that are outside of that. I think Mouse sent me like a PDE question, which is fine. I can try to look at that. It looked pretty hard though, and it was also in Portuguese or Brazilian Portuguese. I'm not sure, so I might need a translation on that. But right, let's raid Don. Yeah. Can you do the raiding? I'm not sure how to raid. I'll probably have to ask you. Is that something you can do? Let me stop the recording here.